So how do vertex normals help us shade 3D geometry? Take a look at these three different spheres that I have here in front of me. This is just a default sphere brought into Blender. And as you can see, it's made up a bunch of faces, a bunch of quads, and it looks like this. As faces that are more direct to the light are brighter, and faces that are further from the light are darker. But the transition between the different faces is not very smooth at all. Each face is just sort of calculated how bright it would appear. And that's because the geometry does look like this. These are these separate flat sections. So if we want the sphere to look smoother, like we can see on this one over here, we need to figure out a way to blend the brightness of these different faces. And while directly just blending the brightnesses around vertices is one approach, it's kind of outdated. We do something a lot more clever nowadays. And that all falls under the category of shading. Before we talk about shading, first let's just take a look at this sphere, which is simply the same thing that's been subdivided a few times, and it just has a lot more geometry, a lot more details, but it's still flat. It still has these separate flat faces. So one solution to make our sphere look better and not look so chunky is just to add a lot more geometry. Turns out that's a pretty expensive solution to the problem. So instead, what we can do is we can back up and think about the core problem and the reason that it's looking chunky. And then if we can solve that underlying problem, then maybe we can convince the computer to render everything smoothly shaded as we see here. So let's take a look at the core issue that we're dealing with. So we have two faces from the side here I'm drawing. And these faces have different sort of normal directions that are facing outward. And every single point on that face shares that same normal direction. So when a beam of light is sort of being simulated, and in this rendering engine it doesn't even simulate it, but like directly, it's not like drawing, it's not ray tracing. But as we are attempting to simulate how light interacts with objects, we are paying a lot of attention to the angle that the light is taking as it bounces off of the object. Because light coming very steeply to an object is going to behave differently than light that is coming straight at the object and bouncing away. And roughly, in a very diffuse surface, it sort of determines how much light energy hits the object, how bright it becomes. A curved surface that's like infinitely curved, I say infinitely, just actually curved and not, made up of some infinite number of faces, that would have the light would bounce off of every single point slightly differently. And it could do that because every single point on the face is facing, on the surface, is facing a very slightly different direction. So because the bend sort of smoothly transitions, the way the light bounces off of it appears to smoothly transition. The core issue is that our underlying geometry doesn't look like this. We would have to add so many points to make it look like that. Instead, it looks like this, which is not as many points. So the solution is something called Vertex Normals, which is what allows us to take geometry that looks like this and have the computer render it as if it looked like it was curved. And the way it does that is by, for every vertex, hence the term vertex normal, for every vertex, we give it a normal direction. And if this face has this normal direction, and the vertex has this normal direction, and the other vertices on the opposite side of the face have that direction, what we can do is, instead of using the face's vertex direction for the light as it hits every single point on that face, and the light hits this point, and it hits something with that face, and hits this point, hits that same angle, instead, we can tell the computer that even though the point it's hitting is in this location, is still on that flat face, we can tell it that it is actually angled slightly differently. And we can do that by taking these two, these two vertex normals and sort of calculating what the angle of those, what the corresponding angle in between them would be using interpolation. And that's kind of it. So let's take a look in Blender of what that actually looks like. So here is our sphere that's been shaded smooth, and we can see it has those smooth shadows. But if we look at the edges of it, they still look flat and chunky. And and that's exactly right, because there's no actual geometry filling the spaces here. It's not actually curving around the edge. It is still flat. I cannot draw with a trackball mouse. That's why I have a drawing tablet. Okay. So on our flat surface, on our flat sphere, let's take a look at the actual normals. We can do that here. We can turn them on. So here, these are the edges, the normals of the faces. So this is just the face direction, but we can use, instead of rendering with that information, we can render with the vertex normals. And it looks pretty weird, but let's take a look at just one face sort of in isolation. So for the face, we are given each vertice a direction. And right now the direction is the same as the face itself. And we're doing that for every single face, and that's why these vertices have these 4 lines sticking out of them, because it has these 4 different directions sticking out of them. If instead we were to tell the computer to, hey, render this as smooth and not flat, and just click a button and turn on all the shading, if I were to look at these vertex normals again, I would discover that there is no longer 4 of them, there's just 1 of them. And now our let's just look at our sort of extended example here. And now if we had something like a 90-degree turn, so on this vertice, we're pointing out in that direction. On this vertice, we're pointing out in this direction. And on this vertice, we're pointing out in that direction. And as we draw the light rays hitting these faces, turn the face ones off. As we draw the various light rays sort of hitting these faces, it could, look at the 4 different vertices and find the point of the space and find that sort of the average direction and say, hey, I'm facing in that direction at this point. And then the point next to it, I'm facing in some slightly different direction. And at the point next to it, I'm facing in some slightly different direction, and so on. And when we do that, if we take a look at how this, how this 90-degree turn looks, it doesn't look very good, but across our, let me just delete this. Oops, trying to use shortcuts for the wrong software. All right, there we go. Across the entire sphere, it looks pretty good. So let's consider a cube. And let's see what happens if we blend a cube, right? So the cubes have these faces, but if we say shade that smooth, ooh, that doesn't like, that's not very cube shaped. So it's not perfect. When you get really sharp edges, it tends to be weird. One solution might be to just add a bunch of detail. And you can see now it looks better in some angles and worse in others. And it turns out we actually only need that detail right at the edges. So now it's got like kind of a beveled edge look, even though in the geometry it doesn't have a beveled edge at all. Just because it still looks weird, but we can zoom out and it's fine. I mean, it's not fine, it still looks bad, but better. So get away, cube. So that's a short version of vertex normals. When I render this as flat, it shows me this much more confusing sort of split normal view is what that's called. It can still calculate the vertex normals just by averaging the normals of the faces all around it, and that's basically it. And then just either choose to ignore it or not. So behind the scenes, the rendering is a lot more complex. But I mean, there's a lot more trickery going on than just that. But that is what vertex normals are doing. is they are allowing the computer sort of treat this as a curved surface in terms of how it is reflecting light, even if its location in space is in the same one location that's flat. And if that seems like trickery, if that seems like cheating, just remember that we're on a computer here. Everything's fake. None of it matters. It's all trickery. So yes, it is cheating. But that's just a weird perspective to have about it. You know, it's all fake anyway. So anyway, that's a little bit about vertex normals. I hope that helps.